Bismillahirrahmanirrahim. Greetings. Following up on the previous lecture in which I verbally discussed the concept or the difference between derivative and antiderivative as two independent functions or differential and integral functions. In this lecture, I intend to demonstrate the concept pictorially using graphs and diagrams. Now, using the analogy of known examples to infer about unknown concept is a very good strategy in problem solving and also conceptually understanding the subject. I have made a video about this subject, about this concept, and I strongly also encourage my students to learn that art, which is really art. And so in this lecture, I may also select an example to follow so that we can better comprehend the concept. Okay, then, let me stay out of way and put the material on the bulletin board, and we go over that as I have written. May I do that, please? Okay. Okay. Now, here, this is the graph of derivative function, some derivative that we are going to go. In fact, I selected to be f of x to be x squared, that we are very familiar with, parabola, and the derivative of that to be f prime of x to be 2x. I'll go over that shortly. Now, here, the derivative function is a function, has input and output. So when I give the value of x in its domain or in a given interval, he gives me an output, which is the height of this graph. Now that output is the slope of the tangent line or to the graph of the original function that we don't know of, we call it a mother function. And we can also say is that instantaneous rate of change at that given point x. But this derivative only gives us the slope of the tangent line to that graph. It doesn't tell us in what point of the graph this the slope is such a thing. Do you follow me? So the derivative only provides us with the slope of the tangent line. Now, one reason is that there is no unique mother graph. There are infinitely many members of the same family that they have the same slope at the input x, or the same instantaneous rate of change at the given point x. There are infinitely many of them. And therefore, we cannot pinpoint a single one of them. So how we do, we are going to go over that. So are you comfortable with that? Let me go one more time. The input that I'm giving, this is the graph of my derivative function. It gives me the slope of a tangent line. It does not tell me what the value of x is on the graph of the original function, on the graph of the mother function. It does not tell me what. And the reason is, as I mentioned, I have also graph of that. I put it on for you so that you can see the reason for that. One reason, in fact. And I suppose this needs a little bit to be I have to zoom this one, I suppose. Okay. Now here, notice that when I give the derivative of a function here, he gave me a slope of a tangent line, graphically, is that right? But there are infinitely many members of the same family that the slope of a tangent line at this input is same. I draw some of them. Some of them are above the x-axis, as you notice. Some of them are below the x-axis. And there are infinitely many of them that because the constant of integration indicates that we can pinpoint which one we want. We learn about that later on. All right? So for that reason, when I give the input for my derivative function, is not going to give me a unique model graph. It doesn't tell me what the model graph is uniquely. So I cannot get information in that sense from what? From the derivative of my function. It only, I keep repeating, it only gives me the instantaneous rate of change at this given point, at the x1 given point, not at x1 f of x1, not at the point on the graph of the original function. And this is one reason. You can see that there are infinitely many of them. We will go over that later on also. So let me put the next one and zoom that one back. Sorry for my primitive equipment. Huh? I have a cheap camcorder and somehow I'm conveying the message. Okay, hopefully it's clear. Now here, what I said, let me read it again. I put it in writing purposely, that using the analogy of known examples, in this case I make only one example, to what? To infer about unknown concept. It's very good, a strong strategy to use in problem solving and comprehending the subject very well, comprehending the subject in detail. Now, I'm going to do the same thing here. I'm giving x1 as an input to my derivative function. The derivative is an independent function as input and output. The point is that the input for the derivative of function is also the same input for the original function. All right? Now, when I give the x to the derivative function, he gives me the slope of a tangent line to the graph of the mother function that I don't know yet. Do you follow me? So I know the slope of a tangent line, or I know the instantaneous rate of change of the function at that input, not at the input and output of that. You follow me? Okay, next will be this one. Now here, a slope times rho equal to rise. As a matter of fact, I have put that in the first lecture. Let me go over that one more time for you, for all of you that you may have forgotten. I draw a right triangle. Now the relation of the sides of right triangle is not the same as relation of Pythagorean theorem. I'm not talking about that. just to remind you that ratio of what rise over run is the slope of this line. Is not the numerical value of that line. Is not the length of that line. It is a slope of that line. So a slope is a number. So a slope times run will give me what? Will give me rise. Because we have a ratio. A over B equal to C. That means what? B times C equals to A. So I'm using that, that analogy in a sense. Do you follow me? We have already mentioned about this in the first lecture. Now here a slope times run equal to rise. Is that right? Okay. Now the length of the rise is what? Is infinitesimally small at each point. So I get a slope, I multiply by run at this particular point on the graph, and I get the rise, but a slope, run is extremely small. As a matter of fact, we go to the, we dive inside the infinitesimal point. Infinitesimal word that, as I said, only mathematics can go, and we bring us a lot of good information. But a slope times run give me rise, and rise is what? Is infinitesimally small. All right? So I wrote that one here. Then rise at some point given x equal to x1 does not tell us about what is f of x1. I keep repeating, that is the fourth, fifth time I'm saying that because it's very important observation. It does not tell me what is the value of function, the mother function at x1. So here, the goal, what is our goal? The goal is to determine what will be f of x1. We know f prime of x1. From that, we want to infer, we want to understand, we want to find out what will be what will be the f of x1. So that's what we are after. Okay, next one is now next one is this. Let me have this one. This is the graph of a derivative function. In our example, let's say it's a prime of x equal to 2x. We do not know what is the graph of f of x. All right? Now, I give him a value, let's say x1. The derivative, the height of this, the y value, the output of the derivative is what? Is the slope of a tangent line. All right? Now I multiply a slope of a tangent line by what? By the run, I get what? I get rise. So I start from the very left end point of the interval, and as I mentioned in the previous lecture, like people, they're standing on the top of the shoulder of one another, and I find out that the graph, the f is somewhere here. All right? Now I do for the second point, let's say x2, and end up to be here. I put that x3 end up to be here, x4 end up to be here, and so on and so forth. And then when I go here, the function in this case is my function is an increasing function, so I end up with these points, all right? And so on and so forth. Now, here I'm giving the value of x1, x2, x3. The derivative function give me the slope. I multiply the slope by what? By the run. He give me rise. And I put the rise on the top of each other each time that I go. One after on the top of one before, and they are all infinitesimal. And I end up with a skinny line segment, that if I connect all these points, the graph of the function will take over. The concept that I just mentioned is absolutely beautifully correct, but unfortunately doesn't tell us what f of x is. is not wrong, is very good, and it is the idea is as important as a matter of fact, is the first step of discoveries is the idea. So this gives us good information, but does not help us to find f of x. So we go and see some other way to do it. You follow me so far? The next one is this. Let me cover that one. I'm sorry, I forgot to bring the card with me. Just 1 second, if I may. Let me cover this one, and then we come to that. Now here, my function is f of x equal to x squared. You see, I graphed it. This is the graph of f of x equal to x squared. Now in 1D demonstration, just as an example, 2 times 3 equal to 6 is the length of a line segment which is 6 units long. That's what we can interpret 2 times 3 in what, geometrically in 1D. You follow me? So here, a slope times tangent line, a slope times rho is the product of 2 numbers. So we can consider that as a line segment, which is the rise, and we did discuss it in the just a second ago about what the handout that I had about that and didn't help. Now we want to do it some other way so that we can come out of we can somehow find the mother function out of it. Now, the other way to interpret this one, 2 times 3 can also be interpreted in 2D as what? As an area. As an area of a rectangle 2 by 3 dimension. Again, I repeat myself, 2 times 3 can be interpreted in 2 ways. One is that in 1D, 2 times 3 equal to 6 is the what? Is the length of a line segment which is 6 units long. In 2D, 2 times 3 is the area of a rectangle which is what? 6 square unit. You follow me? Now, I start from the very end of the given interval, the left end of the given interval. I start from that, and I give the value to the derivative function. He gives me the slope. I multiply the slope by rho. Notice that I multiply 2 numbers. And 2 numbers, when you multiply them, geometrically, interpretation of that is the what? Area of a rectangle. Now, the rectangle which is here is infinitesimally small. Infinitesimally small. Is in what? Is in the word of the midget, in the word of infinitesimal, in the word of points. So I exaggerated that. I took it up and zoomed in. I brought it up all the way to the right so that you can pictorially see what's going on. All right? So what I do, I give the x value to my derivative. The outcome of the derivative is the slope of a tangent line. Is that right? Is a number. I multiply that number by rho, which means I'm multiplying product of 2 numbers. And product of 2 numbers in 2D is area of a rectangle. So therefore this will give me what? Area of this rectangle, which belongs to here. I brought it up so that we can see it better visually. Do you follow me? Now I do the very same thing for the next point, and next point, and next point. And in mathematics, there is no such a thing as a next point. We are going really deep into the subject that imagining them. So for the next point and next point, we get area, and we put them next to each other, and the accumulation of those areas, which end up to be the area under the curve of the derivative, end up to be the mother function. Isn't that fascinating? It's like a miracle. It's fantastic. It's beautiful. It gives you wings. Do you follow me? I don't have to repeat again, huh? You can pause your computer. You can think about it before you continue. All right, I'm a little bit even hesitating so that you get the chance to do that and think. Contemplate, think, reflect, so that you perfectly conceptually understand the subject. Now, let me go to the algebraic analogy of that. Let me cover this one so that we can get them step by step. Here, we are translating the visual demonstration that I just made, is that right, into algebraic, to see what the algebraic outcome will be. Demonstration into algebraic yields the following. Now look at this one carefully. Limit of f of x plus delta x minus f of x over delta x, we know what that is from the first lecture, second lecture. Limit of that as delta x approaches 0, we said that is derivative, that is definition of derivative. And I repeat myself, this definition can also be proven using, in fact, delta epsilon, very similar to what is it, a limit that belongs to the real analysis. So in every calculus textbook, they call this one what? They call this one definition. But I repeat again, this definition can be deductively proved, that we call it what? Deductively proved, that becomes a theorem. But anyhow, when we take the limit of this, we get the derivative, we multiply by delta x as delta x approaches 0, and what do we get? In 1D, we get the rise. In 2D, we get what? We get the area. Is that right? We already went over that. Now, there is a catch here. What is the catch? Is the algebra. There is the algebraic whole. What is that algebraic whole? Is that delta x and delta x, they cancel each other algebraically. So we are left with f of x plus delta x minus f of x as delta x approaches 0, so we end up with f of x minus f of x, which is 0. The idea was beautiful, but did not hit the dead end algebraically. So we have to seek another way somehow to explain this one, to come back to that. And what I do here is this. Let me go over this one. So here, if I go over that, the limit of that, and add them up, I end up with 0. I already mentioned that, all right? All right. Now, what I do is that I put from I equals to 1 to n, which means I divide my interval into n equal sub-intervals in a sense. Again, I will be going over them in detail for the coming lectures. And then now, this time I use the derivative that has already been achieved, which means we already know the slope of a tangent line, meaning limit of f of x plus delta x minus f of x over delta x as delta x approaches 0, we have already achieved that one. And that is what? That is f prime of x. Then we multiply that one by delta x, which is the length of the interval, let's say b over b minus a over n, as n becomes extremely large. So that delta x in this case, becomes extremely small. All right? And that is what end up to, they call it Riemann sum, that again I will be talking about that in the coming lecture. And that will be when I take the limit of that, as n approaches infinity, I end up with definite integral. Fantastic. And also there is another way to say that instead of saying n approaches infinity, we can say that the mesh or the norm of the partition approaches zero. And there is much more advantage of saying it that way, because then the b minus a over n, the interval from a to b does not have to be divided into equal subintervals. We can divide it as we wish, and when we say the mesh of the partition approaches zero, that gives us a better mathematical interpretation of that and what's going on, to come back to this when we take the limit of that. Again, that is for the coming lectures. I'm just waving my hand. Okay, let me now zoom back and say a few words before I close this. Okay, the point is that if the subject is a little bit, if you are hearing that for the first time, as I mentioned in the previous lecture, for the first time, please do not get discouraged. The subject is very, very simple and beautiful and sweet. And I'm intending to upload possibly 10 or even more lectures just about this subject before I go through some other topics. So I'm going to make it very explicit and clear for you. But the conceptual understanding of the subject is very important. So please try to conceptually understand. Do not memorize, do not follow recipes, and dive into the subject. That will not only bring the anxiety, so-called, of mathematics out, but also makes the subject is very interesting and you fall in love with it. It's a fascinating subject. Okay then, as always, I thank you for watching, and I hope that my lectures are beneficially and productive to you. Again, I keep repeating at the end of each lecture that if you have any comments, if you have any suggestion, please share it with me. Feel free to do so in the comment section below, and your comment, your suggestion will be a great favor to me. Okay, then I thank you again for the second time, and as always, I wish all of you prosperity, good health, and happiness. And stay and remain in good health. So long. I always give an army salute. So long.